states that when a current carrying material when a current carrying material is placed in transverse magnetic field then an electric field is induced in the material. Electric field is induced in the material in the direction perpendicular to the direction of both electric both perpendicular to both direction of current and magnetic field. Suppose the material is placed here if in this material current is flowing in the direction x and a magnetic field B is applied in the direction y, then an electric field will be induced in the material in the direction either in positive z or in negative z. Means electric field will induce in the direction perpendicular to current and magnetic field. The angle between current and magnetic field is 90 degree. So we can say that this current carrying material is placed in transverse magnetic field, and if this current carrying material is placed in transverse magnetic field, electric field will induced in the direction perpendicular to both current and magnetic field. This is the statement of electric. Now we will study exactly what is happening in the material so that electric field is induced in the material, and also we will see the application of Hall effect. Applications are important as far as examination point of view. When current carrying material is placed in transverse magnetic field, a force acts on the charge carriers in the force acts on the charge carriers given by vector equal to Q into V cross V, where V is velocity of carrier and V applied magnetic flux density. This force F is called Lorentz force. Lorentz force, and for this Lorentz force we are interested only its direction. We will see actually in which direction the force is acting. First case for holes, the velocity in the material. If current is flowing in this direction, the velocity for holes Vp will be in this direction. In this direction, velocity of Vp will be in this direction, and the magnetic field is applied in the perpendicular direction in this direction B. So direction of velocity and direction of magnetic field is known B. Now we can calculate the direction of Vp cross B so that the direction of force can be calculated for a hole. Using right hand rule, we can calculate the direction of Vp cross B. If we use right hand rule to calculate the cross product, direction of Vp cross B comes out to be in the downward direction. So force acting on the holes given by Q into Vp cross B will have direction in the downward direction. So we can say that when a current carrying material with the direction of current shown in the figure and direction of magnetic field shown in the figure, the force will act on the holes in the downward direction. Now number 2, for electrons. In this material, again we are letting the current flow in this direction and magnetic field is applied in this direction. Due to the direction of current in this direction, the electrons will flow in the opposite direction, or we can say that electrons flow in the opposite direction of current. So direction of electrons will be in opposite direction. In the opposite direction, is electrons will be moving in the opposite direction of the current. So we can say that this is the direction of electron velocity and this is the direction of magnetic field. Again we have to calculate Vn cross B. We are again interested in the direction of Vn cross B. So using right hand rule, direction of Vn cross B can be calculated using right hand rule, and according to right hand rule the direction of Vn cross B is upward. Last time it was downward for holes, but this time it is upward for electrons. Now force acting on electrons is given by Q. Charge is negative for electrons minus Q into Vn cross B. The direction of Vn cross B is upward, but as electrons are negatively charged carriers, this negative sign will reverse the direction of force, and for the upward direction of Vn cross B and negative sign of electrons, the force again will act on the downward direction. So we can conclude Fp and Fn both have downward direction. So this direction of force will help us to determine the direction of electric field which is induced in the material. Now we will place a metal here. This is metal. In metal, charge carrier is only electron. There are no holes in case of metal. If current is flowing in this direction, and magnetic field is applied in this direction, then the negatively charged carriers in the metal will experience a force in the downward direction, and these electrons will settle on the downward surface of the material. And now I can say this surface will be negative with respect to this top surface. And if I measure the potential difference between top and bottom surfaces, then I will definitely uh, experience a difference in the potential. This surface will be more positive as compared to this surface, and I can say that a potential difference will be induced between top and bottom surface, and this potential difference is called Hall voltage. This potential difference is called Hall voltage. If top surface is more positive than bottom surface, then electric field will direct in from positive to negative, and this electric field is called induced electric field. Induced electric field. This electric field is in the downward direction for metals. Now we will change the type of material and we'll see the direction of electric field again. Now we have placed an intrinsic semiconductor. In intrinsic semiconductor, again current is flowing in this direction and magnetic field is applied in the perpendicular direction. As these both are simultaneously applied to the material, the charge carriers in the material will experience a force. We have already shown that electron and holes both experience force in the downward direction. So these electrons will settle in the downward on the bottom surface. Also, the positively charged carriers holes will also settle on the bottom surface, and in at this bottom surface the electron concentration N and the hole concentration P both are equal. As both are equal, we can say that on the bottom surface of this material net charge is zero. So there will be no potential difference for intrinsic semiconductor. V is equal to 0 volt and E will be equal to 0. There will be no electric field induced in case of intrinsic semiconductor. So if we know that this material is semiconductor and we make a current flow through it and apply a transverse magnetic field, and if electric field equal to 0, then we can conclude that this material is an intrinsic semiconductor. So we can determine the type of material by observing the Hall voltage and electric field induced in the material. Next case, we will place an N-type semiconductor. Again, if current is flowing in this direction and magnetic field is applied in this direction, in N-type semiconductor, the electron concentration is very greater than hole concentration. Now, if current is flowing and transverse magnetic field is applied, the electrons and holes both experience a downward force. Electrons will settle down and also holes will settle down. But as far as the concentration is concerned, we can say that electron concentration is very greater than hole concentration. As electron concentration is very greater than hole concentration, now I can say that bottom surface is more negative as compared to top surface, and again potential difference will be developed here, for which top surface will be more positive than bottom surface. Top surface is more positive than bottom surface. Electric field will direct from positive to negative, from top surface to bottom surface in the downward direction. So in this material there will be an electric field which directs from top surface to bottom surface. Now we will place a p-type semiconductor. Current is flowing in the same direction and magnetic field in the same direction. Now for p-type semiconductor, the hole concentration is very greater than electron concentration, and as the hole concentration is very greater than hole electron concentration, after the charge carriers settle at the bottom surface, we can now see that the hole concentration at the bottom surface is very greater than electron concentration, P is very greater than electron concentration, and as P is very greater than N, so we can conclude that the bottom surface is more positive than top surface, so all voltage will develop with bottom surface more positive. This is the all voltage for p-type semiconductor. This time bottom surface is more positive, then the electric field will direct in the upward direction. Electric field will direct in the upward direction. So for intrinsic semiconductor E equal to 0. For n-type semiconductor, E directs in the downward direction, and number 3 for p-type semiconductor, E has direction upward. Note if direction of I and B changes, direction of I and B changes, direction of E will also change. So this was exactly what is happening in the material when a current carrying material is placed in transverse magnetic field. Now we will see some equations related to Hall effect which can be asked in the examination. Problems can be asked in the examination. The Hall voltage developed in the material is mathematically given by Vh equal to Vi Rh upon W, where W is the width of material this dimension, and B will be the thickness of the material, I is the current flowing through the material, and B is the applied magnetic field. I is current in amperes, B magnetic flux density in Weber per meter square or Tesla, and W is width of material, RH is called Hall coefficient. RH is the reciprocal of charge density. Reciprocal of charge density. And charge density can be written as charge Q into carrier concentration N or P. RH equal to 1 upon Q into N or P. Its unit is meter cube or centimeter cube per kilo. This is one coefficient. The electric field induced in the material is mathematically given by induced Hall voltage divided by thickness of the material. V from application of electric. First, we have already seen the first application. We can determine the type of material. Number two, we can calculate the carrier concentration. For example, for N-type semiconductor, Vh equal to B I R H upon W. In this equation, B I W are known. Vh calculated using voltmeter and RH can be calculated. And we know that RH equal to 1 upon Q into N for N-type semiconductor and P for P-type semiconductor. So N equal to 1 upon RH into Q. Using this equation, we can calculate the carrier concentration in the material. Number 3, application number 3, Hall effect can be used to calculate the mobility of charge carriers. Mobility of charge carriers using the equation mu equal to sigma upon RH. Number 4, it can be performed to design a multiplier which multiplies B and this was all about Hall effect. We will solve one problem which was asked in GATE examination. the majority carriers in an N-type semiconductor have an average drift velocity v in a direction perpendicular to a uniform magnetic field B. The electric field E induced due to Hall effect acts in the direction A V cross B should be along V, option C B cross V, and option D opposite to V. In the problem, N-type semiconductor is given. In N-type semiconductor, uh, suppose this is an N-type semiconductor. Current is flowing in this direction. If current is flowing in this direction, electrons are moving in the opposite direction. So direction Vn will be in this direction. And magnetic field is applied V in this direction. So for this material, direction of velocity will be this and direction of magnetic field will be this. The force acting on the electrons will be equal to minus q into v cross v, and we have already calculated the direction of force, and the force will be in downward direction. For n-type semiconductor, electrons will settle at the bottom surface. The electron concentration will be more as compared to hole concentration. So the electric field will direct from positive to negative. That will be in downward direction. E will be in downward direction. Now we will see out of this four option which one has downward direction. Opposite to V will be in this direction because V in is in this direction. Along V will be in this direction. This direction is not matching. V cross B, Vn cross B. If this direction is calculated using right hand rule, will be in upward direction. So V cross B as direction in upward. These two directions are not matching. So B cross V. If we calculate B cross V according to right hand rule, we get a direction in the downward direction. We get the direction of B cross V in the downward direction. So this electric field and B cross V has the same direction. So we can say that in N-type semiconductor, the direction of electric field is same as the direction of B cross V. Now we will say the two types of semiconductors. One is called direct band gap semiconductor. Direct band gap semiconductor and indirect band gap semiconductor. Number two is the indirect band gap semiconductor. These two types are divided on the basis of the energy released during recombination. See, when a covalent bond is broken, an electron move from here and become free electron, and this is the generation of hole and electron pair. Generation of electron and hole pair. Out of these, this electron lie in conduction band and this hole lie in valence band. So we can say that there is a huge, large energy difference between these two charge carriers. When an electron and a hole recombine, energy is released in the surrounding. This energy can either be in the form of heat or in the form of light. For this semiconductor, direct bandgap semiconductor, the released energy released during recombination is in the form of light. So we can say that if the energy is released in the form of light, the semiconductor can be called as direct bandgap semiconductor. Example for direct bandgap semiconductor are gallium arsenide, indium phosphide. Second, if the energy is released in the form of heat, the semiconductor is called indirect bandgap semiconductor. The semiconductor is called indirect bandgap semiconductor. Example for indirect bandgap semiconductor are germanium and silicon. Last one, a small topic is Einstein equation. Nearly 3-4 times questions have been asked. This has been asked on this Einstein's equation. Einstein's equation state that the ratio of diffusion constant for electron to mobility of electron is equal to diffusion constant of electron by mobility of diffusion constant of hole by mobility of hole, and these two ratios are equal to Vt, where Vt is called thermal voltage, and this thermal voltage is written as Kt, or sometimes it written as Kt by Q. This Kt by Q is equal to this Q. From this equation, we can say that d by mu has unit volts, or mu by d has unit volt inverse. This question was asked once in GATE examination. Also, we can say that d upon mu equal to k into t. So we can say that d upon mu is directly proportional to temperature, or mu upon d is inversely proportional to temperature. Using this equation, d upon mu equal to kt, we can write its relation with temperature. The The thermal voltage Vt is written as KT, where K equal to 8.6 into 10 raised to power minus 5, and T is temperature in degrees Kelvin. Putting these values, we get T equal to T upon 11,600. At T equal to 300 degrees Kelvin, it's at room temperature. Vt is around 0.0456 volts. This can be written as 25 millivolt, or sometimes it is written as 26 millivolts. We will solve one problem on this. Calculate diffusion constant for electron in silicon material at T equal to 300 degrees Celsius. Assume mu1 equal to 1300 centimeters square per volt second, and Vt equal to 25 millivolts. We know that dN upon mu1 equal to Vt, so dN equal to mu1 into Vt equal to 1300 into 25 millivolt into equal to 52.5 centimeters square per volt second. The simplify